erase these. If you go a little bit closer to this what? This tree. Let me really highlight this now. Right? This is a what? That's a 3. All right, get the other stuff out of the way. And when you, the whole idea of this concept of limit is, if you went really close to here, aren't you closing in on here? You follow me? It's that simple. That's what we're saying. The more tighter you bring it in here, you're getting closer to what? The actual limit. L is limit. And if you just keep bringing delta, and we're saying, as long as you keep getting this distance, you can't be a distance of equal to 0, but you're always what? Very, very as close to 0 as you can. Infinitely small. Cool? Thanks. Hey, you okay if I don't even put that problem on a test? You know, hey, trust me, I could give you 99s in a row. Wouldn't you get it anyway? Sometimes, I know. So I probably won't even put a problem in that section of this. But thanks for bearing with me on that. I just want to make sure you're good with that. We get a half hour a lot for us to do that stuff, right? Cool.
What's the use case for this?
Oh, great question. That's the whole idea. I mean, mathematician, I used to be on a listserv, and it would pop up every year. The title would be Delta-Epsilon proofs. And which teachers what? Would do this, and this, and I think this is great. We should show this. And the one area I would say I would totally agree with them is, let's say a student in this class is going to be a pure mathematician. Now, pure mathematician, that's all they're going to do is math proof. And it's all they're going to do in their undergraduate degree, probably their junior and senior, a lot of math, sophomore year too. Master's degree is going to be all pure math, which is all proof. So they might get into this stuff. You start talking about, it's just a theory behind it. But if you say beyond this, are you going to need that for calculus 2? No. Are you going to need it for calculus 3? No. Are you going to need that for a differential equations class? No. But that would be the only one. If we're looking for a benefit, is a student who's really into pure math and curiosity about the theoretical realm there. That's it, though. That's it. I mean, seriously. Other than that, that's why you notice, again, you know, now you know why 30 math colleagues in my math department decided how much we can allot to this. Did they give it an hour? No, not even an hour. They only went with what? Half hour. They're stopping. Just half hour. Just do something. I'm like, okay, we'll talk about it.
Isn't this like the difference quotient?
Yep, it's just like the difference quotient. That's coming up. That's coming up. We won't get to it today. So, hey everyone, thanks for bearing with me on that. Unless you wanted me to put that on there. You're like, no, put it on there. We'll just take the smaller one. Fill it up. Yeah, I know. Hey, last thing we're doing is continuity. Again, this is not a long section. It really isn't. Which one was big? 2.3. That was a lot of algebra. This one ain't that big, but I want to go back. I want to see if we can come up with the definition of continuity. So I'm just going to make a picture like I had the other day. I just had a graph like this, right? I'm going to put a hole here. And when this is x equal to 1, and this is the y value 2, okay? I got a hole here though. Does everyone see my hole? Now I got a dot right here at 4. My question is this, before we get into continuity, 2.5 is on continuity. Ready? What do you know about the limit as x approaches 2 from both sides? All right. For the limit as x approaches 2 to exist from both sides, the limit as you approach from the left side has to equal the limit as you approach from the right side. All right. As you approach x, oh, not x equal to 2, x equal to 1. 1, I apologize. So as you approach x equal to 1 from the left side, what y value are you getting closer and closer and closer to? Where that distance, oh, I use delta, right? Delta is like infinitely small. Delta is close to a 0, right? From here. But you're getting closer to 2. Now delta on the other side is close to 0. You're getting closer to a what? 2. So what's this answer? Does everyone agree? If this is f of x here, I forgot to put the f of x here. Let me just step away. Does everyone agree for my graph? Is this true? Yes. For that graph right there, we know that. True? We're going to come up with a definition for continuity. Like, let's come up with a statement that says, this is what's necessary for a function to be continuous. Continuous means connected. Connected. C-O-N-C-O-N. Continuity? Would you think connected? C-O-N-C-O-N. Every time you hear the word continuity or continuous, think it's gotta be connected. Well, everyone, is this graph connected at x equal to 1? No. So let's talk about it. What would simply make it connected? It's that daggone dot. It's way up here. Where would it have to be? Aha, so we're saying, get out of here. For this thing to be connected, this hole would have to be what? Filled in. True? Okay, I'm going to do it right now. So if we're trying to define continuity, and for a function f of x to be continuous at x equal to 1, because everyone, can you tell it's continuous everywhere else? I'll put an arrow. Isn't the function continuous everywhere else? Let me make sure that doesn't overlap there, because then it wouldn't be a function, right? You just put an arrow like that. F of x, in order for it to be continuous at x equal to 1, the limit as x approaches 1 of f of x would have to equal, fill in a blank. What do you think? Someone's going to come up with this. Remember, it wasn't continuous, right? It was a hole. It was way up here. But we said to make this continuous, we'd have to have this hole what? Filled. So I'm putting a dot here. Now, do you notice that one? I'm playing around with f of 1, right? That's what I'm doing. I moved f of 1. This is x equal to 1, but I moved f of 1. So we're saying, for a function to be continuous like this at x equal to 1, the limit as x approaches 1 of f of x has to equal f of what number? There you go. Thanks for being with me. This is what we're talking about. This is what makes a function continuous, by that statement. Now, we could put one in the textbook like that. We would just have to change number 1 to some letter. You want to make up a letter? Give me another letter.
H.
H. Here goes, all right, H. Oh, don't use H, because they always use H with different portion. How about C? Will C work? That one? All right, so here we go. Let's make this statement now for all functions. The limit as x approaches C of some f of x, then what would have to be true? It would have to equal what? F of C. Isn't that cool? I know, I was like, maybe I should have them do that on the test. I just wanted to show you that. So,
That would be the thing.
that's funny. What do you think? I was thinking about it, Joe. I was like, yeah. I think it's more fun, but I noticed how you came up with this. That's what I want you to see. Like, in math, sometimes you go, how do you define something? This is how you define it. So that's why they put the continuity section after what section? The limit laws and limits. It follows limits. It's the idea. You need limits to define continuity. Do you follow me? To say everything will be as long as this is true. The limit as x approaches every value c on the function of f of x will equal to what? F of c. Cool? Awesome. Hey, let's do one. But I want you to focus on where's the function discontinuous. Alright? Where is f of s discontinuous? 3 more problems, and I want to make sure we do 3 more. Not a long section. Alright. Are you ready? Some of this class is going to be quick. I want you to list the x value. So I should say at what x value? At what x value? Is f of x discontinuous? What should we do? Should we graph it? I mean, should we go through the graph and all this? Hold up, I think you all know. Where's this graph not connected? You bet. Don't make it harder than it is. Do you all agree? We have knowledge of graphs like this. This graph is undefined at what value? That means it would be nothing existing there. Well, the graph has to be continuous everywhere and not have any breaks. Well, there's a break at 7, so what's the only answer? At x equal to what?
Joe, I think we should put that in the test though, right?
Yeah, right, you agree? Hey, the only thing is, you know what sometimes people do? They think it's at -4. -4, it's okay, you all agree? That the function exists there. It's just the what? Where they call it, there's an asymptote there, isn't there? So focus on the denominator, right? And heck, if that denominator had 2 expressions down there, then use both of those. You know, if this bottom had a what? X minus 7 and an x plus 3, what would be the other value? There you go. That's the idea. Alright, here's my next one. I want to go to page. This was a good one. Then we're going to put a number down. Alright. Everyone, this is like number 45. It's on page 129. Like number 45 on page 129. We'll change directions. For what values of C? Is f, function f, everyone, continuous on the interval -infinity to +infinity? Question mark. Or what value is C? Alright, they gave you a piecewise, everyone. They got a cx squared. And they got a plus 3x there. Alright. And x squared, oh, I apologize, an x cubed. X cubed minus cx if x is greater than or equal to. I'm wrong on the side. Are those trees? Yeah. I apologize. There we go. Cx squared plus 3x, x cubed minus cx. Now everyone, if I hide these, do you agree these things are nice smooth curves? These are cubics, these are quadratic, aren't they smooth everywhere? So really, to make this thing work and continuous everywhere, we're really concentrating on what's going on at what x value. What's the critical value? 3. Do you all agree? Everywhere else, this thing should be safe. But we're trying to solve for what variable? C. So let me reiterate this, and you're going to give me a suggestion. I'll make this problem a very easy question. I mean, I'm talking, we're not even going to make a graph. I just want to make this thing continuous everywhere. Well, that's a parabola. Even though it's got a constant c in here, make that a 2, a 5, and 8. That thing's going to be nice and smooth everywhere. So that's a cubic function. We're only worried about it this what? The 3. We want to make sure the function is connected at x equal to what? 3. So what's your suggestion? Insert 3. Substitute x equals 3 into both equations and solve for what variable? C. Someone got that? Very good. Let me say this again. Simple math problem. It may look confusing. We're like, let's take the value of x equal to 3, plug it in there, plug it in there, plug it in there, plug it in there, leave the c's, set them equal to each other, and solve for what value. See? Because that means the two values are going to be the same y values, right? This y must equal this y at x equal to what? 3. Does that make sense? The two y values must be equal at x equal to 3. Do you follow me? Alright, let's do it. Plug in a 3 in here, what do you get? C times 3 squared plus 3 times 3 must be equal to, okay, I'm done there. What's this side? 3 cubed minus the c times 3. Solve for c. This will work. Alright, what's 9c plus 9? Is that right? 3 cubed. 27, thank you.
How do you solve that? 12C? What's 27 minus 9? My answer is 12/8, 18/12 unless we can reduce that. Can we reduce that? What do y'all think? 18/12? 3 heads. Or 1.1? 1.5.
Now, how could you check this, Owen? If on your test, you just wanted to check this, and you got like an extra hour, I guess you could pull out your graphing calculator, if you wanted to. Make X what? Make this C value, make this C value a 1.5, and a 1.5, graph the parabola, graph the cubic function, and what should happen at X equal to 3? They should meet. Right? Unless you want to graph piecewise functions. Make sure I do that with calculator. We're all like, don't go through that, we get it, we did it. Hey, can't you do 100 of these in a row? Yeah. What's the idea? We're only worried about here, right? Hey, last problem. You know what I wanted to do last, do you remember? It was that problem I forgot last class, remember? The piecewise one. Let me do one of those. So when I'm looking for one in this section, I know they've got one. And there it is. Kevin? This is number 41. This is on page, it's actually on page 128. All right, here it is. I want 4 values of x is f of x discontinuous. We're okay. I want f of x equals 2 plus x squared. Four minus x.